Hi, everyone. It is my pleasure to introduce Dr. Daniel Shapiro, our third speaker in the AI and autonomy track. Dr. Shapiro is a principal research scientist at the University of Alabama, Huntsville. He has conducted 30 years of research in general theories of cognition, autonomous agents, machine learning, and application of AI in games. Today, he will be presenting updates on research task WRT-1028, validation framework for assuring adaptive and learning-enabled systems. With that, I turn it over to you, Dr. Shapiro.
Very good. Thank you. All right. Before I get started, I want to just acknowledge my colleagues, Professors Brian Mesmer, Nick Jones, and Paul Colopy, all at the University of Alabama in Huntsville. Jennifer Stevens is a graduate student in the systems engineering department there. So today I'm going to talk about steps towards a tool for managing validation arguments in systems engineering. The outline is going to be the following. So first I'm going to talk about validation in systems engineering and the scope of validation activities that we are hoping to be able to address with an automated tool. Then I'm going to talk about the structure of arguments in validation and the notion of how argumentation is a relevant model for the kinds of reasoning that goes on in validating systems engineered artifacts. Then I'm going to introduce 4 specific ideas that enable an argumentation tool. So I'm going to talk about a vocabulary of argument types. I'm going to talk about a template instantiation model that uses knowledge of the structure of arguments to help you form them for validation purposes. I'm going to talk about evaluating argument models into, as I say here, a vector of probabilities over beliefs. And I'm going to talk about extending argumentation models such that they make the handshake with formal decision analysis tools, making decision analysis functional in the context of arguments pro and con particular beliefs. Then I'll talk a bit about related work and next steps. So when I talk about, when I describe validation, let me contrast it with verification in systems engineering. Now these are, there's no thoroughly agreed upon specific vocabulary here, so I will say this colloquially. Verification is the process of determining that an artifact meets stated requirements. So this is fundamentally, there's the design and engineering activity, but the verification part is fundamentally a measurement activity. We see that the properties of the artifact as measured meet a list described on paper. In validation, we're interested in the process, we're interested in determining that an artifact will perform its intended tasks in the world. So this is a very different mind frame. Some of the actual physical activities are very similar, but the mind frame is, will it perform in the world? So that brings out different properties of validation. In particular, it involves stakeholder preferences. So I am a geologist. We are sending a rover to Mars, and I care that it can perform the function of taking samples and doing experiments on rocks. It requires judgment calls so that I, as a geologist, may decide that this artifact is valid, but I as an exobiologist or as an exochemist, may just say that no, it's not. So it requires judgment calls on the part of the stakeholder. It also concerns abstract properties about artifacts. So when I am designing an artifact for, like designing the rover for use on Mars, I am well before the point in which I've actually built a physical rover. However, I am concerned that my design decisions will lead to an artifact that will perform well in its task on Mars. So in the early stages, these are very abstract claims. And then and they are also prospective. It is about a future artifact. I'll make the point that the environments that we're deploying these engineered artifacts in are often partially modeled and understood, which also goes further to the point that we can make statements, we can make claims about what that artifact will do, but those claims have to be a little bit general with respect to, in order to encompass the unknowns about those environments. Lastly, I want to make the point that a system can meet requirements and still not be valid. So again, this example of the rover that meets all of its requirements but does not, in fact, appear valid from the eye of a particular stakeholder. Then the role of validation, or the scope of validation in the view that I'm presenting here, it's not just when you have a final artifact in your hands that you can probe and test. Rather, we're interested in a view of validation that begins at program definition, moves through design, and into end of artifact evaluation. So here, the notion of argumentation becomes powerfully relevant. So in the beginning, at program definition time, we might have reasons and counterarguments, arguments and counterarguments as to why the program is needed at all. When we get into artifact design, we might have arguments and counterarguments that the program is technically feasible, that it is that the design will produce the intended capabilities. Earlier still, we may be concerned that it's financially feasible, as again, arguments pro and con. That would be earlier in program definition. As we get into end artifact evaluation, we'll have arguments and counterarguments that the end artifact will in fact perform the intended tasks. So this notion of argumentation is applicable at various stages in the lifetime of a systems engineering project. Here's an example of what I mean by validation. And so this is the kind of target representation that we intend to support. And let me orient you on this figure. So we're going to pick this up midway. We're somewhere in the design process of building a rover to go to Mars. One of the claims that we would very much like to make is that the rover will successfully execute tasks on Mars. And we might justify that by saying, well, the rover will successfully execute tasks on Earth. We have some collection of observations that we've made so far. Something about slippage, something about average speed, something about the wheels, and that they're able to withstand their expected loads. And we've gotten to the point where we've actually taken some actions here on physical tests. So we've built a physical model of a wheel, and we've run some tests on fracture strength. We've also done some modeling and simulation work at the point at which I'm depicting this diagram. And that modeling and simulation work has come to certain conclusions. The blue arrows here are all support relationships. The red arrows with the X's on them are defeating links. And so what this is saying is that I ran a test of fracture strength on a physical model, and it refutes the claim that the wheels can withstand the expected loads. However, I've also got a result from modeling and simulation that says the wheels can withstand those loads. But in addition, I have an expert who has said that that modeling and simulation test is not valid for certain reasons. So we have a collection of arguments, pro and con, and we have a collection of reasons, rationale, or justifications, another word, why that stitched those arguments together, why we should believe that the wheels can withstand the expected load. Well, we've got expert opinion in one case, modeling and simulation results, test and fracture strength results, so we've got test results. These are the rationale that form arguments. So this is a sense of arguments pro and con. I'll come back to that structure. I'll come back to that structure a number of times. So argument models, let me walk through the internal parts of them. So Toulmin developed argumentation models, and they contain claims, premises, evidence, and warrants. Here we've got a claim, wheels can withstand expected loads, premises in green, warrants in purplish. The claims and the premises and evidence and Toolman models we can think of from a computer science perspective as encodings of beliefs. So beliefs, however they're represented, for example, in a relational logic, but beliefs are statements about the world, which we're arguing over whether they should be true, whether we should believe them or not. Warrants are justifications, reasons why we should believe the claims given the premises. Warrants can support or attack premises. They can also support or attack what are claims on the output side of warrants, or other warrants, and these structures can be hierarchical, as I showed you, or build a graph structure of these, as I showed you in the previous slide. I want to spend a moment talking about warrants as what they are, and let me relate that they are proof standards. So they're reasons why we should come to believe something, and then we use those in everyday life quite a lot. Now, in the old days, there was a form of proof which was trial by combat. Like, I'm here, I'm right because my champion is stronger, when they fenced off. We don't have that one so much anymore, unless you count, corporate mud wrestling, over who's got the baton. But trial by combat was at one point in human history a standard of truth. Proof by sigil, we use this all the time. A recognized authority says it's good. Doctors say that taking vitamin C is good for you. And therefore, many people believe it, take vitamin C. Proof by social norm, we've always done it this way. Try standing in an elevator facing the back instead of the front, and you'll see the effect of the social norm not working, working against you. Proof by demonstration, we run into this all the time. Very corporate. 3 billion have been sold, therefore it's a good thing, you should buy one. A 30-year track record. We've been building them this way for 30 years. It stood the test of time. A flashy example. I am selling new Apple products, and we're famous for putting out marvelous, flashy demonstrations. Here's my favorite, proof by pumpkin. Many years ago, on my PhD dissertation, I connected a learning system to the giant pumpkin plant in my backyard. And I was teaching, the system was learning when to mist and when to water in order to get an enormous pumpkin. And I planned to bring a 600-pound pumpkin to my thesis defense, cover it with a tarp. And when my committee said, does it generalize? I would grab the tarp, lift it off and say, there's the proof, ta-da. And nobody argues with a 600-pound pumpkin. So, it's a proof by pumpkin. Now, silliness aside, this also illustrates the point that warrants, standards of proof, come in some form of a specialization hierarchy. There are types and subtypes. So now I'm going to move on and talk about that particular idea, that there are types and subtypes in a small vocabulary of warrants. So I'm going to make the conjecture that systems validation employs a small vocabulary of warrant types that capture engineering standards of proof. And they can be represented by a hierarchy with inheritance of what I'm going to call critical questions that determine whether the warrant is apt, whether the warrant applies. So much like that list of proof standards, some of which are relevant for engineering arguments, here is a top level of a hierarchy. There's one more on the next slide. But at the very top level, warrants come as agreement, forms of agreement, forms of inspection, forms of analysis. The last one will be forms of construction. But agreement, I can ask, is the claim subject to agreement? So we cannot, the value of pi is not subject to agreement despite, I believe it was the Illinois pi law, or was it the Indiana pi law, but back in the late 1800s. So, if the claim is subject to agreement, then we have several subtypes of agreement: attestation, assumption declaration. Attestation is asking for, it's for an appeal to a certification by individuals or collectively the group. So expert opinion is an example of an individual attestation, and we'd want to know if the expert is relevant to the claim or not. And if the expert is not relevant to the claim, then that warrant does not apply, and we shouldn't utilize any of the claims for or against that come from it. So we have critical questions which are inherited down this tree. Attestation, common knowledge, does the rule apply in this context for everything that is a piece of common knowledge? In general, there are exceptions. Assumptions, is the claim that we're making via assumption reasonable? Is it material to what we're trying to assert or conclude in the end? Is it convenient? So these are properties of assumptions that govern any assumption that you might make. Inspection is going off and actually looking at some artifact prospectively, or if you've got the artifact in front of you. Demonstration is representative of the use case. Is the demonstration representative of the use case? But the idea is that we're proving via demonstration that something is has a particular property, etc., with tests. Analysis, I gave an example of analogy in the large slide. We were reasoning from performance on Earth to performance on Mars, so that definitely has a role in systems engineering, modeling and simulation, raw inference. Here, proof by construction is the notion that I can do something to make a claim true. So safety assurance cases are an example of proof by construction, which I've labeled a kind of a procedure. So will executing this procedure produce the claim in this context? So to prevent the rover from going wheels up on a rock, I can execute particular procedures about what destinations I will give it, and I'll test them at Earth. So what destinations I'll give it and what destinations I won't. Is it a way of enforcing a claim by taking action? So safety assurance cases are a kind of proof by procedure. I'll mention one more here, delegation, which applies specifically to the case of autonomous artifacts. I'd like to know, okay, in a very technical sense, I can prove to you from work that I've done in the past that if an agent, an autonomous agent, for example, and the principal, me, its user, are value aligned in a specific technical sense, I can prove to you that the agent will perform as best as it possibly can for me in the target environment, and that guarantee precedes learning. So that means I've got an agent, it doesn't have much by way of any capability yet. I work on its value structure, the criteria by which it makes decisions. And after its learning is said and done, I know that that agent will do the best for me it possibly can in that environment. So I'm happy to talk more about that, but not in the context of this talk. Moving on to the next idea, constructing validation arguments. So if we know something about the structure of arguments in validation, and we know something about the claims, we can build an editing system that helps you instantiate validation arguments. So one thing we can do is select warrants appropriate to a claim. So here, what I'd like to do is bolster my notion that the rover will successfully execute tasks on Earth. So I can go through the hierarchy of argumentation types and say, well, I think I can do that by analysis and by inference and by some logical inference over a collectively exhaustive set of cases. So there's an inference, and the system can guide me through filling in, what is a collectively exhaustive set of claims or premises for this particular warrant of inference that meet that templated form. Similarly, I can select warrants in response to critical questions. So here, is the claim subject to analysis? Is a property of agreement? It's a critical question of agreement. And for the subtype, are the source and target environment tasks and systems sufficiently close? For the subtype of analogy, that is a critical question. So we can prompt the user, and the system can, through experience, highlight particular options as the most relevant. Here comes expert opinion, and we choose it, we lay down expert opinion, and we continue to work through the elements of expert opinion. So here, a template instantiation method for assisting you in the construction of validation arguments. Moving on from template instantiation, the third idea is about evaluating argument models. So here's an argument model that has red refutation links, blue support links. The rounded rectangles are claims or premises, but they are beliefs. And the hexagons are warrants. So I've got many, many one, many kinds of relationships. I've got refutation and support relationships. We'd like to evaluate these. And the task is to determine what to believe given conflicting rationale. So we've defined a mechanism where you can identify a probability distribution over beliefs represented in an argument model. This is somewhat novel relative to the way argument models are used in the literature. They're typically used to identify one preferred belief, the thing that you should most believe in the current circumstance. Here, we're using them to identify an entire vector of possible beliefs, and in fact, a probability distribution over those. This works out to be one equation applied recursively to assess the probability of beliefs and that warrants are apt. I'm going to describe that in the next slide, but we're going to associate a probability with the model that is a warrant for driving conclusions. So here, this is a very Bayesian approach. It says we're going to determine the probability of our top claim Y as the sum of the conditional probabilities of Y given each of its antecedents, the vector of antecedents and their truth values, times the probability of those truth values. So that's a straightforward Bayesian calculation. We can come to the probability of Y. However, the pill that you need to swallow there is about warrants and what does it mean to assess the probability of a warrant. A warrant is apt if it is a relevant model for drawing conclusions in the current context. So we're used to this in linguistic contexts. So here's an example, the classic example that Ernie is a bird, Ernie can fly, because we make the inference all birds can fly. But we know that there are exceptions to that rule. So penguins don't fly, and young birds don't fly, and abnormal birds don't fly. So we'd like, so can we say that Ernie can fly? So if all you know is that Ernie is a bird, when I ask you to assess whether the warrant is apt, I'm going to ask you to assess the probability that all birds can fly is a good model for drawing conclusions about Ernie. So let's say you haven't explicitly represented the notion that penguins don't fly, young birds don't fly, and abnormal birds don't fly. Now, I'm asking you to make that call. Is the warrant all birds can fly relevant to Ernie? And that calls on you to pull out of your background knowledge, to assess your background knowledge abstractly and say, 0.6, I'm not going to see an observation that invalidates this inference. Formally, what we're doing here is we're assessing the probability that no observation will invalidate the defeasible inference represented by the warrant. At the risk of belaboring that point, let me say that this assessment is independent of the warrant's conclusion. It's not about can Ernie fly or not. It concerns the applicability of the model relative to background information. And so this is the same dance that people do when you assess the probability that it will rain tomorrow given the weather that you see today, because there's lots of things out there that may affect, that are unrepresented, that may affect your assessment of the probability of rain tomorrow. And you unconsciously sum over those as you make that assessment. So given the premises of a warrant, now that's the act of describing that a warrant is apt. Now more in the details, given the premises of the warrant and all combinations of arguments against it, how likely is the warrant apt? So here we have this, we have a warrant, which is analogy, and we want to sum over the probabilities that the warrant is apt, given that the rover will successfully execute tasks on Earth or not, times the prior probability that the rover will successfully execute tasks on Earth. If I add, in this case, a counter argument from expert opinion, now what I do is I just increase that sum. So now I'm concerned that, does this analogy hold if the rover will successfully execute tasks on Earth and I have an expert opinion as a counter argument, or if I have no expert counter argument, but I still have the rover will successfully execute tasks on Earth and all the other combinations. So the point is that I'm making that sum, and it requires a certain amount of user assessment to be able to do that. There are a variety of simplifying assumptions that we can access, but that is the game, that is the name of the dance that we're asking people to go through here. Going through the rest of the elements of the architecture, I can determine the probability of a leaf premise by just directly assessing it. Is Joe a reliable expert? In a simulation model, I just am given those things. I state that the material is a particular alloy of aluminum and the max RPM is 5, etc. In determining the probability of a non-primitive claim or premise, I once again perform the same thing. So I find the probability that wheels can withstand expected loads, given all combination of arguments pro and con. Do I believe that the fracture strength test is apt? Do I believe that the modeling and simulation test is apt? So here we once again compute that sum multiplied by the conditional probability multiplied by the probability of the priors, which in turn is, of course, going to get its information from further down the tree. The last of the ideas, adding uncertainties and decisions to argument models. Here we can assess the probability of claims given additional uncertainties that are outside of the information used by any warrant, pro or con. That will let us access standard methods for decision-making under uncertainty, but with the additional wrinkle that we now have conflicting rationale. So here is an example. I've augmented this chart with a cost uncertainty, a schedule uncertainty, a critical design review decision point, and a system test that independently gives me information about whether the rover will successfully execute tasks on Earth. So by performing the same kind of conditional assessment, this starts to look very much like an influence diagram out of the literature, and I can now, in principle, do things like determine the value of the warrant conducting a test. Is it worth it to go off and conduct a test, in this case on fracture strength, in order to, or on some other thing, is it worth it to conduct that test in terms of the net value it gives me for this decision? So that would be a powerful integration of decision theory and this notion of Toulmin argumentation models. Okay, winding up, there is other work, a fair amount of work in this general arena. There are several structured argumentation tools that use Toulmin argumentation type models in the systems engineering environment. So Advocate is one specifically for assurance case development. It's been applied there. ASCII, safety case construction, thing recently in Japan, the D-Case editor, which is a typed editor for assurance cases. More broadly, there's been quite a lot of work, largely out of NASA, on using argumentation theory to construct assurance cases and to generate automatically generate test cases that come out of argumentation models. There are more broadly, there's literature on the relevance of argumentation in systems engineering. I've listed here at the end the value alignment work that I did quite some years ago. There's argumentation more broadly. There are competitions for argumentation models, although not in the Toulmin sense. Arguments there are atomic, and you're interested in what's a consistent set of arguments among all the arguments that are made. And I should acknowledge that a great deal of work in argumentation theory has come out of legal reasoning in a situation where people are possibly disseminating possibly telling the truth, and you are trying to analyze their arguments for consistency to see which ones hold up. So there's background here on argumentation theory and systems engineering. So in summary, our project has made a number of observations. First, validation spans system conception through final artifact evaluation, is a point that we're trying to make. Toolman argumentation models capture validation reasoning for and against claims about systems properties. They represent something, they capture something that you commonly see as engineers meet to argue over whether a conclusion is valid. Validation arguments involve a small number of fundamental warrant types, and they can be composed via a template-based editor. Validation arguments evaluate into a joint distribution over beliefs, and we can combine arguments for or against claims with decision models. So taken as a whole, these particular building blocks enable the next step, which is to work on actually embedding them in a tool for managing validation reasoning in systems engineering. I'm out of time, so I'll be brief here. We build, our next steps is actually to build a prototype editing tool to illustrate the potential benefit from managing the validation process. Those benefits come in the form of an audit trail for arguments made, validation status checks, like where are we in our development so far? What do we know? What do we don't know? What do we believe? Clarity of reasoning, which is a principal benefit of any kind of decision analysis activity, often above and beyond turning the crank to say, what decision you should make. You at least get clarity on the reasoning en route. And then demonstrate the benefit of merging argumentation with decision models. Lastly, documenting our work. So we've got a number of papers to be written. Contact information. We'd love to talk with you about this work. Feel free to contact myself or any of my colleagues working on this project. So with that, I'll stop. Thank you very much.
Thank you, Dr. Shapiro.
Okay.
If there are any questions, please enter them into the chat. I don't see any of them at this time, but I do have a question. So you mentioned that a lot of this work is coming out of NASA. Do any of the CERC sponsors come to mind when you think about this work, or is there more work that CERC can do to contribute to our sponsors in this space?
So I think if Brian's on, I think I might pass the question about other CERC work, because Brian is intimately familiar with the work being done at CERC. I'd pass that question on to him. Brian, are you available?
Don't see him, but he would be able to enter into the chat.
Okay. So more broadly, there's a space here of building. We've been building fundaments, to clarify, how to wrap argumentation models around systems engineering tasks, and we've gone forward to address a number of the key elements there. But now we're in need of synthesis, and that's really the right way forward on this project, is to start building a tool, bump it up against real domain knowledge, a breadth of domain knowledge, and adjust and refine the theory as we go forward. So it very much needs that kind of development to actually try and build that tool or pieces of that tool.
Excellent. We have another question here from Danny Moore. Are you acquainted with some of the persuasion work done by Cialdini?
I am not. The persuasion work by Cialdini. I'd be interested, though.
Danny, if you could share in the chat,
please.
That would definitely be interested.
I'm going to stop sharing my screen there. Okay.
Brian doesn't know how to unmute, but we'll follow up offline. Absolutely, Brian. And the other Brian Nowotny, we can follow up with you as well with some of our NASA point of contacts.
Okay. All right. Well,
thank you so much for your time.
Oh, you're very welcome. I'm very glad to present. Thank you.
Thank you.